In drug development, there's a significant challenge. How do you design a drug to interact with a protein that doesn't have a stable shape? In this explainer, we're going to look at research that uncovers a rather counterintuitive mechanism, one that could change how we approach these kinds of elusive proteins.
So, let's frame the central problem. You can think of traditional drug design like a lock and key. A protein is the lock with a very specific, defined shape. The drug is the key, engineered to fit perfectly. But what if the lock has no fixed shape at all? What if it's constantly shifting? This is the core paradox when we try to target a certain class of proteins.
These shape-shifting locks are called intrinsically disordered proteins, or IDPs. You see, unlike more rigid proteins, IDPs exist as a dynamic collection, an ensemble of different structures. This inherent flexibility has made them notoriously difficult to target with conventional drugs.
To make this difference clear, just look at this comparison. On the one side, you have folded proteins. They have predictable, rigid structures, which is ideal for standard drug design. But on the other side, you have IDPs, which are really a flexible collection of different shapes. It's a moving target, which is precisely why they've long been considered undruggable.
Now, the specific IDP that this study focuses on is called alpha-synuclein. This protein is clinically very important. Its tendency to misfold and clump together, a process we call aggregation, is directly implicated in the pathology of neurodegenerative diseases, including Parkinson's. Here's where it gets interesting. A small molecule called fasudil has been observed to actually slow down this aggregation process. So we have a critical clue. We know it works, but the exact mechanism, how this small key is interacting with that shape-shifting lock, has remained a mystery to science. So, how do you go about solving a molecular mystery like this? The researchers here used an advanced computational approach. Because it's practically impossible to observe these fleeting interactions in real time in a lab, they essentially built a virtual model to watch the protein's behavior with atomic-level precision. Their method involved three main steps. First, they ran extensive simulations of the protein's movements, which generated a massive dataset of all its possible shapes. Second, they used a deep neural network to process all that data and find the most important underlying patterns. And finally, they built a model to map out the protein's most common shapes, and, importantly, how it switches between them. You can think of this last step as creating a detailed shape map for the protein. And the results from this analysis led to a very unexpected discovery. It's one that really challenges the conventional thinking on how small molecules are supposed to interact with these disordered proteins.
The first finding was really about establishing a baseline. The analysis showed that in a simple water solution, with nothing else around, alpha-synuclein naturally tends to favor just three main conformations, or what we call metastable states.
But when fasudil was introduced, the number of distinct states the protein adopted actually doubled to 6. This is the central finding. Instead of forcing the protein into one single ordered shape, the small molecule caused it to explore a wider range of conformations. The researchers refer to this as an ensemble expansion mechanism. So rather than forcing the lock into one specific shape, fasudil is effectively adding more possible shapes to its repertoire. This discovery turns the traditional lock and key model on its head. This, of course, raises a fundamental question. What is the physical principle that's driving this expansion of states? And the answer to that is found in thermodynamics. So, the next step for the analysis was to pinpoint the precise thermodynamic force that's responsible for this increase in available shapes. And that force is something called conformational entropy. Simply put, entropy is a measure of disorder. When we talk about a protein, higher conformational entropy just means it has access to a greater number of different shapes. So, the jump from 3 states to 6 represents an increase in the protein's conformational entropy. Now, what's particularly interesting is where this entropy change is coming from. The data here shows a large change in the protein's own internal backbone entropy, but a negligible change in the entropy of the surrounding water molecules. This is a strong indicator that the effect is intrinsic to the protein itself. So the key takeaway here is that fasudil appears to work by directly tuning the internal disorder of the alpha-synuclein protein. It's not about imposing an external change, it's about modulating the protein's own inherent flexibility. The data also revealed another effect. This table shows the mean first passage time. That's just the average time it takes for the protein to switch between its shapes. With fasudil present, it takes significantly longer for the protein to settle into its most common shape.
By effectively trapping the protein in these intermediate states, fasudil might be preventing it from finding the specific conformation it needs to begin clumping together.
The implications of these findings are quite significant. They suggest a completely new way of thinking about how to design drugs for this entire class of challenging proteins.
You see, the classical approach has always been to try and reduce disorder, to force an IDP into a single, predictable shape. This study suggests that the opposite strategy might actually be more effective, to leverage and even increase the protein's intrinsic disorder.
This really changes the question of how we should approach these so-called undruggable targets, which are often at the very heart of many difficult-to-treat diseases. Ultimately, this research proposes a potential paradigm shift. For intrinsically disordered proteins, the therapeutic goal might not be to create order from chaos, but instead to intelligently modulate that chaos. And that could open the door to a whole new class of therapeutics,